I would like to introduce Francisco Paco Girela, who will be presenting Distributing Time Synchronization in the Data Center. Paco is a business development and sales engineering lead at Safran and is coming to us today from Chicago. This is Paco's first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Welcome, Paco.
Hello. So I'm Francisco Girela, and I'm not a network operator. So I'm not a network operator, but I'm a timing or a time synchronization specialist that has been helping different companies to integrate time synchronization solutions into their networks. Mostly, I've been focusing a lot with financial institutions, high-frequency trading, electronic trading. Also, I have done a fair share of telecom, utilities, or other kind of designs for different industries. So today, I will be speaking a little bit about how to distribute time synchronization in the data center. So let's start by introducing what are the benefits of precise time in this context. So the first thing will be coherency. We have distributed system, distributed databases, bit of information in different places, and you need to have some coherency between all the information that you want to retrieve and that you are storing in different locations. Timing can be a very good tool in order to achieve that coherency, and there are some databases, like for example Spanner, Cockroach TV, that are very aware of that, and that they leverage time synchronization in order to improve their performance. Efficiency. So as I said, I come from the I've worked a lot with financial institutions, pre-scheduling tasks, like for example, if you want to send an order to a stock exchange to buy some market shares, it's important pipelining different assignments, so you are balancing the network in order to avoid overloading, and also some other things, like for example reducing some thresholds for retransmission of packets and stuff like that. So there are papers out there that mention that improving time synchronization has a direct impact on the performance that you can achieve in your distributed databases, minimizing the carbon emissions that you generate in the data center space. Lastly, visibility, and that's probably one of the most typical applications here. You have time, a clock reference in different nodes all across the network. Once that you have that, you can start timing things. When you are sending packets, when you are receiving packets, when the events are happening in the data center, all this kind of stuff, you can do it. And you can leverage that information to optimize and to improve the network that you have. So I wanted to ask a question. How many of you are familiar with time synchronization devices, or have used them in your networks? Okay, very few of you. I mean, that's fair. One thing that happens with timing is that it's a critical part of every network. Every network uses timing, but most people use it as a commodity. They understand that timing will be there. They will power on their computer, their cell phone, they will get time. Oh, it's magic. No, it's not magic. What I want to transmit here is that timing is not only a commodity. Timing can be an asset, and it's something that you can leverage and that you can take advantage to improve your network performance. So if you have one idea to bring home from this talk, please remark that, highlight that. Timing can be useful to improve your network. And what's the complexity of timing? There is one famous quote that says that when you have one clock, you know what time is it. When you have two clocks, you never know what time is it, because they differ one from the other. When we are in a network, we have many clocks. So we have one clock that will be the reference, generating time. You have different clocks all across the distribution network that is providing this time synchronization. You have another clock in the server that is consuming that time, but within the server, you have a clock in the NIC that is receiving the packets. You have another clock in the user space or the virtual machines. You have different clocks on the operative system. So you have a variety of clocks, hundreds, thousands of them, that you need to synchronize all with the other. And there are different technologies to do that. That's a problem, and it's a problem that gets bigger when you scale. So typical fabric that you will find, fabric design for data center hyperscalers, some of them. So multiple layers, your super spine, leaves, then a bunch of servers. And you have clocks for all of them. So when you end up adding all these numbers, you have thousands, hundreds of thousands of clocks in one single building, a data center, and you need to coordinate all of them. So how do we solve this problem, which is a massive problem? We have different technologies. Different parts of the network come with different technologies. Let's start by explaining GNSS. GNSS, you know, GPS, I'm driving my car, I know where I am, that's magic. GPS also provides a time reference, and most people, especially in the data center environment, they use GNSS-based timing from GPS, from Galileo, or any other to have a reference of time in their facilities. The good thing about this time is that it's free, it's almost everywhere, and it's maintained by a trustable source. For example, GPS is maintained by the US Air Force. So you know that the time that you're receiving is correct. The problem is that GPS, GNSS, doesn't work indoor. So you need to have an antenna going to the roof. And okay, you have one reference in one particular place, but you cannot have an antenna for every single device that you have in your data center, right? Additionally, you have very weak signals from GNSS, so they are very susceptible to interferences, to attacks, to any kind of even weather effects that can prevent you to synchronize or to achieve or receive those signals. Once that we have time synchronization in the data center, we have our reference. We know that GNSS cannot cover everything. We need to start distributing it. And there are different ways. First way, pulse per second. Very similar to GNSS, you depend on a RF analog infrastructure to connect to the antenna. In this case, it's RF analog or coaxial cables to connect one device to the other. Pretty good for smaller areas, not so good for scaling, and with a main problem, which is that you send time information, but that time information comes always late because time keeps lapsing and you have a latency on the cables. So you need to calibrate and compensate for those delays. So how do we solve distributing time using analog technologies? Okay, let's create a protocol. I mean, isn't that the solution for everything? So different protocols. We have network time protocol, NTP, basically the timing protocol that is feeding millions of services in the internet, in almost any network. Very good, very scalable. However, it's not very accurate. I mean, it doesn't care about networks. It is integrated in software, so you cannot have this accuracy that in some cases you need. Very good for any human-related kind of service. However, with automatization, with electronic trading, for example, for distributed databases, it's a protocol that cannot provide the best performance. So for that, we move into a different protocol, Precision Time Protocol, PTP, or IEEE 1588 is the name of the standard. A little bit more specialized, it comes with some hardware support that improves the accuracy. And it's a protocol that you can share the same medium with regular data and timing data. So it's something that you can actually deploy in the data center environment. This protocol has been used in a variety of industries so far. What's the problem about PTP? When you are sharing the same devices that you are working with for the production data, you will have buffering, you will have overloads, you will have all the typical situations that you find on your day-by-day when you are managing the network. And all of those will degrade the timing accuracy that you will have with this kind of technology. So we have come to another technology called White Rabbit. So White Rabbit, it's basically the high accuracy profile of PTP. So it's an implementation that guarantees a certain level of accuracy. In this case, sub-nanosecond level. Very specific. It can be used in a similar way than PTP, but typically what we do to achieve this kind of performance is that we deploy in parallel. We have a parallel network for time synchronization where we can guarantee the accuracy and where we can have full control of how timing is deployed. So let's review some architectures and topologies using these technologies. Let's start with a GNSS-based topology. In this case, you have your super spine, you have your spine, your leaf and top of rack, all the servers, and you have one layer of Stratum 1 GNSS time servers. Those time servers are getting time from the roof, from an antenna. They have the RF infrastructure that split the signals and provide that signal to the different Stratum 1 GNSS servers. Simple solution, very scalable. The main problem here is the fact that the Stratum 1 devices, they are not necessarily interconnected one to the other. And that means that if you have different RF installations, you can have different timing in each one of the Stratum 1 servers. Also, if you have those Stratum 1 servers, one of them can be rogue and it's a little bit harder to detect. There are ways to solve it, but it's one of the drawbacks. A quick remark, I mean, tomorrow there is a talk by Oleg from Meta on how they have managed to synchronize their data centers. One of the technologies that they use is this Timecard, which is part of the OCP Time Appliance project. So it's an open community that has designed some technology. In short, a GNSS receiver combined with an atomic clock, all of that in a PCI Express format that you can plug in the server. So a GNSS time server, Stratum 1, that you can plug directly into your server. So I recommend you coming tomorrow for that talk. But moving forward and avoiding doing spoilers, let's go to PPS distribution, right? So the analog way to distribute timing signals using coaxial cables. Fairly simple, legacy way of distributing time, still useful for some applications, smaller collocations, private clouds that care a lot about accuracy and so on. They tend to use these kind of solutions. You have a time server. In this case, it can be a rack format time server. No need to be a PCI Express. It provides the signals to a multiplier, a distributor of PPS signals, and those are inputted to or they are sent to a PCI Express board that accepts pulse per second inputs and which is used to synchronize that server. So, kind of cheap, sustainable in smaller footprints, and also with some particular applications that are interesting. Like, for example, if you have a PCI Express board that can support a pulse per second input, you could, for example, back up the GNSS time server with a very, very, very stable atomic clock. And that atomic clock, it doesn't speak any kind of protocol. The only outputs that it has is pulse per second, is frequencies. So you can use actually this board to re-ingest a very solid failover or atomic clock back to the system. It also helps if you have some kind of traceability. Some devices out there that have pulse per second outputs, you can have these boards in different parts of your network, timestamp when you are receiving the pulse per second, and compare everything. So it's a nice way to prove that your time is fairly good. So moving into network protocols, I focus mostly on the White Rabbit protocol, but this is the same for NTP and PTP. Okay, so what you see in the lower part of the packet exchange in black is basically what happens in all protocols, timing protocols. We have an exchange of packets where we timestamp when we are transmitting, when we are sending those packets, and when we are receiving them. We exchange a few of them, we capture the timestamps, and with those timestamps, we can calculate the offset in the clocks between the different devices in the network. As easy as that. That's the same for all protocols. One that we know the offset, we correct the clock, so both of them actually align. So how do we leverage time synchronization in the data center? So we have a very similar architecture that what we had before, using only GNSS time servers. So in this case, we can minimize the number of GNSS time servers by using a core synchronization network that actually connect to the Stratum 1 servers that you have in place. What are the advantages of that? The advantages is that you don't need that much of an RF installation anymore. You can reach longer distances using these timing protocols, and also the fact that you have a timing protocol can add some redundancy and ensure that all the Stratum 1 are synchronized to a specific level of accuracy. And how do you provide timing to those Stratum 1 servers? So pretty easy. You can do that with PPS, the same that I was showing before, pulse per second. You transform from the protocol to a pulse per second input, and you plug that into the server. Or you can do that if your server has any support for timing protocols. PTP, NTP, White Rabbit, whatever. You can take time from that core network to your Stratum 1 server that is actually doing all the distribution to the subsequent layers. One interesting thing is that, okay, I have a time distribution protocol, so now I don't care about distance. And I don't care about distance, so I can connect longer distances. I can interconnect different data centers. For example, we have a very famous triangle in New Jersey where we have almost all the stock exchanges in the US. So you can actually have the same time in all of them. You can measure all your latencies between all the different data centers and having a single clock notion of time for all of them. One clock domain. You can do that also for reliability. If you are, let's say that you own a hyperscaler, you decide that you need to build multiple buildings because you want to duplicate everything for, you know, disaster recovery and stuff. So you can actually interconnect those devices using network protocols without affecting that much the accuracy. And you can do that using different GNSS time servers in different locations, probably avoiding many of the interferences or attacks that these signals, GNSS signals, have because they are mostly local. Also, you can back up your data center with these very expensive and very accurate atomic clocks, and instead of having 2 or 3 of them per data center, you can have 1 or 2 per region, and what you will do is distribute that through the network, and it's the way to reach those atomic clocks. Again, it's all a little bit of a play on what's the accuracy target that you have. So depending on the protocol that you are using, you will be better or worse in the accuracy. Depending on how you configure your network, you will have a better or worse accuracy. but everything comes with a cost. So typically when we are working with these very big networks, we try to avoid replicating clocks in all the different layers that we have, because that comes with a degradation on the performance. What we typically do is we try to bypass part of the network, so we provide a time reference to the actual time consumers, which is a little bit more accurate. And we try to use some different protocols depending on the application, so the most sensitive parts of your network have a better time accuracy, while the others that only need a reference of time, they can still be served with some other older or more scalable protocols. So speaking about bypassing, you can take time, bypass your spine, your lift switches, and go straight to your top of rack. For example, very high accuracy, you have a parallel network just for timing, you are not messing up with your production network. If you are a little bit concerned about low latency, that's perfect, because you are not adding any kind of traffic. If you are a little bit concerned about cybersecurity, that's perfect, because you are isolating your timing network from your production network, so these devices cannot do any harm. If you want to improve the time accuracy that you need, you want to improve the time budget available for you, because you want to get a lower threshold on the retransmission, because you want to have longer holdover times when you don't have any kind of synchronization arriving to the or reaching that particular machine. If accuracy is important to you, you are time stamping, you are capturing data, you are tapping packets, something like that, this is a good alternative. And also, if you are bypassing your production network, what you can set actually is a supervision network. So you can have a high accuracy time synchronization network, which is kind of your ground truth network for monitoring your data center. So visibility was one of the main applications. If you have a parallel network for time synchronization, that allows you to have probes distributed in your network that can ingest the time that your production network is actually consuming. So actually, it's a combination of both, not only time synchronization for your production network, but time synchronization for your visibility or supervision network, what can help you monitoring your network and ensuring that everything is working fine. So wrapping up, different technologies, you need to synchronize a lot of things, so you have different technologies. You have GNSS, which is the typical one. You can leverage time distribution to link those GNSS. One that you do that, depending on the time synchronization technology that you are using, you can get higher accuracy, you can have a bigger time budget that you can use for whatever you want, including improving the resiliency and the failover capabilities of your timing network. You can leverage your time network to actually create a supervision network in parallel. And the good thing about timing and the solutions that I have presented for timing is that they are typically very accurate, much more accurate than the latency needs that you have in the data center space. So if you have a deployment using this kind of time synchronization technologies, you are probably in the tens of nanoseconds accuracy on the clock distribution. And you don't typically care that much about tens of nanoseconds latencies on the packet retransmission in the data center. So it's a future-proof solution. If you deploy that, make sure that the timing gear that you are getting supports NTP, PTP, these kind of protocols, because this will actually help you testing and supervising your network for a very long time. So this is it. Thank you so much for holding here. Yeah. Thank you.
Thank you, Francisco. Do we have any questions? Okay, apparently no questions. So thank you.
Yeah, you're welcome. Thank you so much.